Okay, we're back now with a discussion of section 3 from chapter 15, and in this mini lesson we're going to talk about esters. Here we see methyl acetate. You recall from nomenclature, right? That's clearly an ester, and esters will not form acyl chlorides. Okay, so I can't take an ester and make an acyl chloride. Okay, think about the reactivity patterns we discussed in the previous segment. But we can take an ester and then turn it into a carboxylic acid or an amide, right? Can't turn it to an acyl chloride because alkoxide is a stronger base than chloride, and the weaker base is the better leaving group. So what do, right? We can take an ester and we can react it with water in what's known as a hydrolysis reaction. And that's an important word to know, a hydrolysis reaction. Okay? A reaction with water that takes one compound and converts it into two organic compounds. There's a lot of lysis types of reactions that are discussed in this chapter, right? Aminolysis is another one, alkolysis, but hydrolysis is a key word to be on the lookout for. Okay? So in that hydrolysis reaction, right, we are taking an ester and converting it to a carboxylic acid and an alcohol. That's the opposite of the esterification reaction that we were doing in the lab, okay, in the design your own ester synthesis. This is the flip side of that. Now, esters aren't super reactive, okay, because it's not a great leaving group with the alkoxide. Water is not an exceptional nucleophile, so we have to use a catalyst for this hydrolysis reaction, specifically an acid catalyst in this case, which is why we see HCl over the equilibrium arrow there. And there's the definition of the hydrolysis reaction that I mentioned before. We can also take an ester and react it with an alcohol. Okay? Notice the product here is again an ester, just a different one. Okay? So this is known as a transesterification reaction. We took one ester, we reacted it with an alcohol, and converted it into a different ester. Okay. Again, a slow reaction due to the fact that we have poor leaving groups and bad nucleophiles. So both of those reactions, the hydrolysis, in this case the alcoholysis, both of those are, again, acid catalyzed, which we see our HCl right here. Okay. What else can we do? I can take an ester, I can react it with an amine, okay, and turn it into an amide. Now notice in this reaction, unlike the reaction we saw before with ammonia and an acyl chloride, we do only need one equivalent of the amine in this situation, okay? Because our leaving group, the alkoxide in this situation, will pick up that free proton in solution. And another thing to look out for in this reaction, right, there's no acid catalyst right here. If we had an acid catalyst, an acid in solution would protonate this amine, and then it wouldn't be acting as a nucleophile anymore. Okay? The amine itself is already a better nucleophile than the alcohols from before, so we don't need an acid catalyst. We usually just need a little bit of heat to drive this reaction forward. So now the question is, how do we do it? Right? What's this mechanism all about to take an ester and convert it to a carboxylic acid and an alcohol? Okay. If we're acid catalyzed, okay, how is this catalyst helping? Okay. HCl, our acid catalyst right here, notice it protonates the carbonyl oxygen. Right? So we get that protonated carbonyl. The question is why, right? I have a lone pair on this oxygen, so I could protonate there. I've also got two lone pairs over here on this oxygen. So in theory, I could protonate in that situation as well, right? Protonate over here. Okay. But our acid is always going to go to whatever atom has the greatest, our proton is going to go to whatever atom has the greatest electron density. And if I think about the two resonance contributors for my ester, it's clear, right, with this minor resonance contributor, right, that this oxygen has the greatest electron density, right? With that negative charge in the minor resonance contributor, greatest electron density, this is going to be the one that gets protonated. And there are two new slides that I've added here. These are not in the full chapter slides. They are on Blackboard. they weren't in there because I have mentioned them in lecture in the past, chapters 9 and 10. We talked about this, and even to a lesser extent last semester. Okay, but I did pull them out and put them here just so you're paying attention to this for chapter 15 and every other chapter moving forward. If I am working in an acidic solution, something's acid catalyzed, that means that I cannot have anything in that pot that's negatively charged. Okay, so all organic reactants, intermediates, products, everything, if it's in an acidic solution, has to be either positively charged or neutral. Okay. Flip side of that, same thing. If I have a basic solution, everything, reactants, intermediates, products, has to be neutral or negatively charged. I cannot form a positively charged species in a basic solution because it would just immediately be deprotonated. So with that in mind, what does the acid catalyzed ester hydrolysis look like? Notice in this reaction, we've got a lot of equilibria that we're dealing with. Okay, so we'll talk about there at the end. A lot of equilibria to be on the lookout for here. So what's going on? Okay, my acid protonates my carbonyl oxygen, like we just talked about. And then if I'm converting to a carboxylic acid, right, my nucleophile in this situation is water. So that nucleophile is going to add to the carbonyl carbon, like we saw before, and that gives me my first tetrahedral intermediate. Okay? And notice that's in equilibrium with its deprotonated form, where I just had a base come in and take off the proton. That is also in equilibrium with tetrahedral intermediate 3, because if I bring in another proton, because keep in mind, I'm in acid catalyzed, I'm in an acidic solution, so I've got some protons that are available. If I take tetrahedral intermediate 2 here, I could protonate down here on the OH, which would take me back to tetrahedral intermediate 1, or I could protonate on my methoxy group over here, my OCH3. That takes me to tetrahedral intermediate 3, okay? Because those are going to be really similar in pKa to one another. Once I'm in tetrahedral intermediate 3, the collapse of that intermediate, I'm going to wait for the slides here to disappear, that takes me over to my protonated carboxylic acid, deprotonate that, and then I get the carboxylic acid product. Had I gone back up here to tetrahedral intermediate 1 and collapsed, that would just take me back to my reactants, and I start all over again. Okay? And that's what I was referring to at the beginning, right? With all these equilibria to consider, how can I drive this reaction forward to actually get an appreciable yield of the carboxylic acid and not just keep going back to the ester? And we think about Le Chatelier's principle from last year. I can force an equilibrium forward, right, by adding more of the reactant, because a reaction shifts away from an increase in concentration. So if I add more of one of my reactants over here, specifically add more water, that will drive the reaction forward and increase my yield of the carboxylic acid. And that's what this slide is telling us right there. Okay? Another way that you could help drive this reaction forward is take your alcohol product. If it's a low enough boiling product, okay, you just distill away that alcohol as it's formed. Remember, a reaction shifts towards a decrease in concentration. Okay? So if I'm distilling something off, I'm again driving the reaction forward. With that in mind, let's talk a little bit more about how an acid helps catalyze these reactions. Okay. We saw that an acid helps by protonating the carbonyl. Okay. Why does that help this reaction specifically? Remember, a catalyst has to help speed up the slowest steps of the reaction, which in our situation isn't shuffling a proton around. Right? It's forming the tetrahedral intermediate and then the collapse of the tetrahedral intermediate. And the acid catalyst actually helps both. Okay. When I've protonated my carbonyl, sorry, I jumped ahead too soon there. Okay, when I protonate my carbonyl here, that positively charged oxygen that I get as a product is more strongly electron withdrawing than is the neutral oxygen over here. And if this is more strongly electron withdrawing, that makes my carbon a better electrophile. So that helps form my tetrahedral intermediate in the first step. Second step in the overall reaction scheme, okay, after I protonate the carbonyl. What about the collapse of the tetrahedral intermediate? Well, if I protonate my leaving group, that decreases the basicity of my leaving group. And remember, a weaker base means I have a better leaving group. Okay. So I help both of the slowest steps in the reaction. There is one special case to pay attention to in these reactions, and that's if I have a tertiary alkyl group. And that does change the mechanism by which we get our products. We still get the same products that we would anticipate, right? You take an ester, you hydrolyze it, you get an alcohol and a carboxylic acid. Okay. But if you have a tertiary alkyl group on your ester to begin with, like we do right here, okay, that changes our mechanism to go via an SN1 mechanism. Okay. Same first step, protonate my carbonyl. But then after that, my leaving group completely departs, right? Jumping down here to form this tertiary carbocation. And here we've already gotten our carboxylic acid. Now I have my tertiary carbocation. Okay, water comes in and attacks that carbocation. I deprotonate, and that's where I form my alcohol. So again, same products that we would predict, but a different mechanism if and only if you have a tertiary leaving group over here on your ester. So what other reactions do we have? We mentioned the transesterification before. Okay. Reaction of an ester with an alcohol to get a different ester. Okay. It still requires an acid catalyst. We mentioned that before. The mechanism, we're not even going to bother showing in this situation. Same mechanism, right? All we've done is change this from an HOH to an HOR. Okay, but the mechanism is identical. Same mechanism, same reasoning, just a different nucleophile using an alcohol instead of water. Okay, but still acid catalyzed. What about using a base? Okay, because I can have a base catalyzed hydrolysis reaction. Okay, where now, instead of water, I have hydroxide. Okay. Hydroxide comes in and attacks my carbonyl like before. I'm not going to protonate it because I'm in basic solution. Okay. Then when I have the collapse of my tetrahedral intermediate, I kick off methoxide, and I'm not going to stop there. Okay, methoxide is a slightly stronger base, so that's going to pull the proton off the end, and I wind up with a carboxylate. So how is hydroxide acting as a catalyst in this situation? Okay. Well, first, hydroxide ion is a better nucleophile than water. So that first slow step is going to be faster. If I have a better nucleophile, it's a faster reaction. It's easier to form the tetrahedral intermediate. And then we're again catalyzing the collapse of the tetrahedral intermediate. It's faster in basic solution because what's shown on the slides here, okay, in an acidic solution, I end up getting a delta positive on oxygen. Okay, but in a basic solution, I never end up with that delta positive on oxygen. And you, of course, know by now that oxygen doesn't like that delta positive. So if you can avoid it, that's better. Okay? In a basic solution, we have a more stable transition state when we collapse our tetrahedral intermediate. Okay? With that in mind, okay, because I form a carboxylate in that situation, okay, here we have an acid catalyzed reaction with HCl. And notice that's an equilibrium, it's reversible. Okay, but because I form a carboxylate here, not a carboxylic acid, this reaction's not reversible. Okay. So hydroxide's not actually acting as a catalyst in this situation. Used that before as an oversimplification. This is actually called a hydroxide ion promoted reaction. And when you hear that word promoted, okay, you think about it like a catalyst. It's making the reaction faster, but when it's using the word promoted instead of catalyzed, that means that the hydroxide ion is actually getting consumed as part of the reaction. Okay. So if you take an ester, you see hydroxide, okay, it's still going to make that reaction faster, but you're going to wind up with a carboxylate, and it's not reversible. Okay. And if you're trying to do a transesterification, You can also make that reaction faster by using a negatively charged species, okay, but you're not going to do it with hydroxide. Hydroxide wouldn't help you in this situation. If you're trying to make this reaction faster, catalyze this one, what you want to be using is the conjugate base of the alcohol. Okay, so here in this situation, ethanol is the alcohol we're trying to put on our ester, so we get this ethoxy group over here. To catalyze this, we would use ethoxide. Okay, the conjugate base of the alcohol you're using in your transesterification reaction. So that wraps up our discussion about esters, which involve alcohols in this situation. Okay, we will pick back up next with a discussion of carboxylic acids and nitriles.